Hello everyone, welcome to chapter 15, Kinetics of a Particle, Impulse and Momentum. In this module, we are going to discuss conservation of linear momentum for a system of particles. The objectives is first to understand the conditions for conservation of linear momentum for particles. When do I apply this conservation of momentum? And then I want to apply this conservation of momentum in addition, this is important, in addition to the principle of impulse and momentum to solve problems. So we're going to use both of them. Now, conservation of linear momentum. If you remember, the principle of impulse and momentum used to look something like this. Summation of linear momentum plus summation of impulses will equal to summation of linear momentum, the final one. So there's a change because of these forces. When the sum of external impulses acting on the object is zero, so I have different forces are giving me impulses, but these forces will give me not zero impulses. Their summation will give me a zero value. Then I can cancel this summation of impulses, and I end up with conservation of momentum, meaning initial summation of linear momentums should equal to the final summation of momentums. This important equation is referred to as the conservation of linear momentum, and this conservation is usually applied when particles collide, interact, or let's say I have an explosion where a particle is separated into two particles and so on. So this conservation of momentum is applied when particles collide or interact. And interact could be, for example, I have a tank that explodes, it becomes two parts. So this is a type of interaction. Now, you need to identify forces and determine in what direction linear momentum is conserved. Keep in mind that the principle of linear impulse and momentum is a vector quantity. So usually we write it for x, y, and z. Now, doesn't necessarily mean that all three could be conserved. I could have a problem where the conservation of momentum happens only in the x-axis or only in the y-axis. So I'm going to identify forces to find in which direction I have conservation of momentum. Internal impulses are usually cancelled because these are equal in magnitude and opposite in direction, and they are cancelled only and only if I consider the whole system. If you consider only one particle, then you have to include these impulses. Now, non-impulsive forces usually are small forces that take place in a short period of time. For example, like the weight of a ball. How much does it weigh? Does not change much. So this weight of that ball is going to give me non-impulsive forces. Impulsive forces are usually large forces that act for a very short period of time, like explosions, accidents between cars, and so on. So let's consider the two objects shown in this figure as one system. So I have MA going to the right with a velocity of VA1. I have block B going to the left with a velocity of B. By inspection, I could establish the direction of the conservation of momentum. And I'm going to see that when the two hit each other, I'm going to assume that they move with a shared velocity V2 to the left. Therefore, the forces acting between them, these internal impulses, they cancel. Therefore, I have conservation of momentum along the x-axis. So I want to write the equation. First of all, apply conservation of linear momentum. Let's say I choose left as positive, okay? And since block A was moving to the right, then I'm going to have MA minus VA1, it is minus since it's going to the left, to the right, plus MB VB1 should equal to the total mass times V2, because they are moving with the same shared final velocity. And this, if I have initial velocity VA1 and VB1, I can use this equation to find the final velocity V2. What if I asked you to find what is this average impulse, AB, acting between the two? In this case, what you need to do is that you need to isolate one of them, either B or A, one of them. Take one of them alone and apply principle of impulse and momentum. So you can do mvp1, and I use p as in particle, so it could be any particle, A or B, plus the average impulse times time, don't forget to multiply the time, equals to the final linear momentum, and this velocity is the one that you find from this equation. So we'll start with one example. You have a 200-gram projectile fired with a velocity of 900 meters per second towards the center of the 15-kilogram wooden block, which rests on a rough surface. That means not moving, resting. If the projectile penetrates, that means it goes through, as you see on the right figure. So it penetrates and emerges, and that means leaves the block with a velocity of 300 meters per second. Find or determine the velocity of the block just after the projectile emerges. As you can see, since the projectile will penetrate and leave the block from the right side, you can see that the block will start moving. So find at what velocity does it move? What is that velocity? Also, it asks you to find how long does the block slide. How long means time, not distance. So find the time. So how long does the block slide on the rough surface after the projectile emerges, before it comes to rest again? So how long will it be moving until it stops? The coefficient of friction is given to you as 0.2. So the first thing that we do here is that we start with the free body diagram. So if we draw the free body diagram of the block and the bullet, both of them. So let's look at the block, and I'm gonna put the bullet in here as well. Okay, so for the bullet, I have the weight. Okay, and I'm gonna call it the projectile, so it's WP. And also I have the force acting from the block on the projectile. It's gonna call it F. Now let's look at the block. I'm going to have the weight of the block. I'm going to have the force acting from the projectile or the bullet. Okay. Also, I have the normal force. And since the block is going to move to the left, I have a friction force to the left, mu k times n. Okay. And I'm going to establish that x is positive to the left, y is positive upward. Okay. So next thing is, you can see that if I consider both the bullet or the projectile and the block, that I have a conservation of momentum, okay, along the x-axis, because both of them will have these impulsive forces that are equal in magnitude and opposite in direction. Now, you might say that the friction is still there, so it's not conserved, yes, but we are talking at the instant when the bullet hits the block, not after it emerges or as it moves, because this friction force appears only when you have movement. So I'm talking about that I have conservation of momentum before movement happens, once the projectile hits the block. So let's write the conservation of momentum in the x-axis, and it will be clear to you why this is not included when I write the equation now. So it's going to be m projectile v projectile 1 plus m for the block, velocity of the block 1 should equal to, okay, after it now emerges, I'm going to have m p vp2 plus m block vb block 2. Now it will start moving. This is the velocity where it will start moving, so still there is no friction. So start with the first one. The bullet has a weight of 200 grams, so it is 0.2 kilogram, and it has a velocity of 900 meters per second, plus originally the block was at rest, so this is 0, should equal to 0.2, and the bullet emerges with a velocity of 300, okay, and then plus the mass of the block is given as 15 kilogram, and velocity is now unknown, and I want to find it. So if I solve this equation, it will give me that velocity of the block should equal to 8 meters per second to the right. Again, I'm solving the problem between two locations. One, this is as it hits the block, and part 2 is basically just when it emerges. So now the block will have this velocity, now it will start moving, now I will have this friction force. So still it did not appear yet. So I solved the first part of the problem, which is determine the velocity of the block just after the projectile emerges, as you can see. Now, it says how long does the block slide on the rough surface after the projectile emerges before it comes to rest again. So now the block will start moving until it stops. So back to the problem. I'm going to draw the free body diagram for the block alone. Okay, so I have the weight. Now there is no impulsive forces. F between this and the projectile has moved already, so it is not there. Now I have normal force, and they have the friction, mk times n, and this is x and y. Now, to find how long time, that means I can do it by looking at the principle of impulse and momentum. I'm separating block B alone. So I'm going to take upward as positive. Write the equation. It's going to be m. It's only the block, so it's m for the block. V1 in y plus summation of f in y dt equals to m v2 in y. The block moves only horizontally, so this is 0, this is 0. Again, you can use Newton's second law, summation of forces in y-axis directly. It gives you the same thing. So I'm going to have normal force times time. Let me remove the bracket just to make it n times t. Okay, minus the weight, which is you have the weight, which is the mass, 15 kilogram, and the weight the gravity is 9.81. This gives me the weight multiplied by t. The time cancels in this case, and I end up with the normal force equal to 147.15 Newton. Okay, now let's do principle of impulse and momentum in the x-axis. This is positive. I'm going to have m v1x. Again, just write the equation generally to organize your work. dt should equal to the final linear momentum. So I have initially the block was moving. Now initially for me is the one that we found here. So this was after the bullet penetrates, after it hits, this was the velocity, which is now my initial velocity. So it's going to be the weight, which is 15, multiplied by the velocity, which is 8. Then I have only friction force acting, so it's going to be minus the friction coefficient, which is 0.2. Was it 0.2 or 0.25? It's 0.2. So I have 0.2 multiplied by the normal force, 147.15, and don't forget to multiply by the time, which is unknown in this case. So this is the only impulsive force that I have. This should equal to the mass, which is 15, multiplied by the final velocity. Since the problem asks you how long will it move until it stops, then final velocity is 0. And from here you can solve the time simply by counting this, and it becomes 4.077 seconds. Okay, and this solves the problem. And you can see, I mentioned this in the objectives, that we want to use the conservation of momentum along with principle of impulse and momentum. We use them both together to solve the problem. Another example: a 4 kilogram projectile travels with a horizontal velocity of 600 meters per second before it explodes and breaks into two fragments, A and B, as shown in the figure. Those fragments have a mass of 1.5 and 2.5 respectively for A and B. If the fragments travel along the parabolic trajectories shown, each one has its own trajectory. A is going to point C and B is going to point D. Determine the magnitude of the velocity of each fragment just after the explosion. Also, find the horizontal distance where the segment A strikes the ground at C. So we want to solve the projectile motion of A only after we find the total distance. So, first of all, what we do here, since originally the projectile had one velocity, 600, then it was separated after it exploded into two fragments, then I know I have conservation of momentum along the x-axis, because the explosion will give me impulses that will be equal in the x-axis in magnitude and opposite in direction. So I will choose right as positive, and I have m, one mass, v in the x-axis, that's all I have, should equal to mass of A VAX plus MB VBX. I don't know the direction of these, the magnitude, so I'm assuming both are positive so far when I write the equation. Now I'll look into the values. So the mass was originally 4 and velocity was 600. Now this should equal to, now I know from the figure that VA is going to go to the left, so it's going to be negative. So it's going to be minus the mass of the segment A is going to be 1.5 multiplied by VA. The magnitude is unknown, but the angle is given to me, which is 45, and here it is 30. So it's going to be VA cosine 45. B is going to go to the right, so it's going to be plus 2.5 VA cosine 30. Okay, so I can solve this. The only unknown that I have will be, sorry, this is VB. So I have two unknowns, VA and VB. So I can solve or rewrite this just to organize it. So it's going to be 2.165 VB minus 1.061 VA should equal to 2,400. And this is equation 1. Now I'm going to write the principle conservation of momentum in the y-axis. Same thing, I'm going to have M Vy should equal to MA VAY plus MB VBY. Now the projectile was moving only horizontally, so originally it had no velocity in the y-axis. Now the projectile A was moving upward, so it's going to be positive. B is moving downward, so it's going to be negative. So it's going to be MA, which is 1.5. VA, it's going to be sine 45. B is going to be downward, so it's going to be minus, negative, 2.5 VB sine 30. Okay, arrange your work. So this will give me 0, or let's go directly to VB. So this will be, I can calculate this. So this will give me VB should equal to 0.8485 VA. And this is my second equation. So I can solve 1 and 2. Solving 1 and 2 simultaneously will give me that VA should equal to 3090.96 meters per second, and VB should equal to 2622.77 meters per second. So I found the final velocity that we're asked to be. So if the fragments travel along the parabolic trajectories, determine the magnitude of the velocity of each fragment just after the explosion. Now, since I know these two velocities, it asks me to find the horizontal distance where A will strike the ground at C. Now, this final velocity that we found here for A is going to act as my initial velocity for my projectile motion for A. So, as a projectile motion, you can write two equations, one vertical, one horizontal. So let's start with the vertical component. Upward is positive. I have Sy. First of all, you have to consider where you want the location, where you want. So in my case, I'm going to use, let me go back to this figure. So you can choose either this as your origin or this as your origin. In our case, we're going to use this one as my origin. Okay. So back to the equation. So I'm going to write Sy. Okay. So Sy should equal to original location in Y plus V0 Y times time plus half AY t squared. So since this was my origin, then point C is basically down by 60 meters. So it's going to be minus 60. So I'm going to say minus 60. This is at the origin. It's going to be 0 plus the velocity. I already found it for A previously. So it's going to be 30. Sorry. I don't know what this keeps coming up. So plus 3090.96. I'm taking the vertical component, so it's going to be sine 45 degrees times the time to reach for A to reach point C, plus half. Gravity is downward, so it's minus 9.81 times TAC square. If you organize this equation, it's going to give you 4.905 TAC square minus 2185.64 TAC minus 60 equals 0. This is a cubic equation. You can, this is a quadratic equation. You can solve this to find the value for the time. It will give you two values, a positive and negative. Obviously, you take the positive value. So this will give me that T should equal to 445.62 seconds. Okay. Now I need to find the horizontal distance. So I'm using left as positive. I will say Sx should equal to is 0x, I'm using the same origin, obviously, plus v0x times the time. Now, the final distance, I need to find it, I don't know it. Originally, I am at 0 location. Velocity is going to be the horizontal component, so 390.96 cosine 45 degrees multiplied by the time, which is 445.62. Simply solving this will give me that Sx comes down to be equal to 973.96 times 10 to the 3 meters. Okay, and this solves the problem. So the importance of this example shows you that also you can use conservation of momentum along with kinematics, in this case happens to be a projectile motion, to solve for certain outcomes. So always keep in mind that you can use kinematics and other equations along with principle of impulse and momentum or conservation of momentum to solve problems. And with this, I conclude this module. I hope that it was useful to you, and I wish you the best of luck. Thank you.